Welcome back. Suppose the position function of a particle moving on a coordinate line is given by s of t equals 2t cubed minus 21t squared plus 60t plus 3. Analyze the motion of the particle for t greater than or equal to 0. So what tools will we use? The tools that we're going to use include taking the derivative, factoring and solving, and a sign chart. And I'm going to show you, this is all completed, I'm going to show you an example of how we can use an equation and these tools, the derivative, factor solving, and sign chart, to be able to analyze the motion of a particle. And then afterwards we'll solve some problems from scratch. All right, so now if I want to point, so you can see me point, I have my handy dandy arrow there. So here's our question again. Suppose that the position function of a particle moving on a coordinate line is given by s of t equals 2t cubed minus 21t squared plus 60t plus 3. Analyze the motion of the particle for t greater than 0. So here, there we go. Here we have our position function. There it is graphed. And I have it outlined because, and this is in your notes. Because it is like really hard to see up here. So to make it a little clearer, I have it outlined so you can see it better. All right, so here we can describe our motion. All right, so here we have the position function as a positive slope. All right, it's moving to the right. Here we have a horizontal tangent line. All right, our function, our object has stopped, and when the reason it stopped is it stopped turn around because now it is moving to the left. So it was moving to the right, and that's t equals 2. At t equals 2, our function started to move to the left. Again, it stopped at t equals 5. And then it began to move to the right. All right. So there we see our function. All right. And notice that although it moved to the left, it never moved left of the starting point. All right. So the values for the function are never 0. There are no x-intercepts for this function that are greater than or equal to 0. We have 1, it looks like, that is less than 0. We'd have to have 1. This is a cubic function, so there has to be an x. It has to cross the x-axis because the domain is negative infinity to infinity. So we do have an x-intercept for the function. However, that is to the left of 0, and that has no meaning. So our function is never 0. So we're always on the positive side of the graph. The positive side of whatever our starting position is. And although we move to the left, we don't move all the way back to the left. So we're always on the positive side of the number line. That's what we can gather from our graph. Our first derivative, so the position graph gives us so much information. We can see we're moving right and left when we stopped. We can see our relative position to some starting point. Our velocity will give us more information. All right, so now if we look at our velocity function, which is the first derivative of the position equation, right? So s prime of t equals v of t, right? And so the derivative of 2t cubed would be 6t squared. We're just using the power rule here. The derivative of 21t squared would be negative 42t. The derivative of 60t would be 60, and of course the derivative of 3 is 0. So that gives us our velocity function, which is 6t squared minus 42t plus 60. All right, now we can use our tool of solving, and this is factorable. So first of all, we can factor out a greatest common factor. And when we see that, when we pull out that greatest common factor 6, we can see t squared minus 7t plus 10 multiplies to give us 10, adds to give us negative 7 is going to be negative 2 and negative 5. So this has two solutions, two critical points. Right? So our solutions to a derivative is going to be called a critical point. That's where something important may be happening. Right? Those are our candidates for something important happening. In this case, it's our candidate for where our function is stopping. where our velocity is 0. All right, so we have 2 critical points, 2 and 5. So here we create a sign chart. All right, so 0, that's our starting point. Right, so we're not going. There's nothing less than 0, so we're not going to value anything less than 0. I've got my arrow here. 2 was a critical point for the velocity equation, and 5 was a critical point. For our sign chart, we evaluate values in between our critical points because there's not going to be it's not going to change sign again. The only places that we can change sign is between critical points. Right? So everything on the interval 0 to 2 is going to have the same sign. Everything on the interval of 2 to 5 will have the same sign. And everything greater than 5 will have the same sign. And we use a test value, and we just simply plug it into the derivative and see what the sign is. And that will tell us something about our function. So if we plugged in a critical point 1 into the derivative, we'd have -1. We have 6 times -1 times -4. That's a positive number. All right, so that means our velocity is increasing from 0 to 2, which means we're moving to the right. If we plug in a critical point between 2 and 5, 3 is good. All right, and we'd have 6 times 3 minus 2, that'd be 6 times 1, and then 3 minus 5 would be -2. That's going to give us a negative number. We don't even care what the number is, right? We just care that it's positive or negative, and that does give us a negative number. So that means we're moving to the left from 2 to 5. And then if we plug in something greater than 5, such as 6, we'd have 6 times 6 minus 2 times 6 minus 5. And that would be a positive number. And that's supported by our position graph. All right, so notice we were moving to the right until t equals 2. All right, and then the velocity was 0 because we stopped. We were moving from the left from 2 to 5, and then we have a horizontal tangent because our velocity is 0 because the object stopped. And then it moved to the right, and then it'll be continuing to move to the right. And that's, if we look at our velocity curve is showing the exact same thing. All right, so a horizontal tangent for the position function is an x-intercept for the velocity function, right? Because your velocity function gives you velocities. If your velocity is 0, right, where's 0? 0 is on the x-axis. All right, so we're going in a positive direction, moving to the right until we get to 2. And we know that because we're above the x-axis. So if the velocity curve is above the x-axis, then it is moving to the right, moving in a positive direction. If for any values where the velocity curve is below the x-axis, it's moving to the left, all right, or in a negative direction. So we're moving in a negative direction from 2 to 5 because of velocity, and we can tell that because the velocity curve is below the x-axis. Notice that the velocity curve also has a horizontal tangent, right? And it has a horizontal tangent at, looks like it's right between 3 and 4, so 3.5, right? So now let's take a look at the meaning of what we see. So from 0 to 2, based off our velocity curve, from 0 to 2, we're moving in a positive direction. T equals 2, we're turning. You have to stop to turn. At between t equals 2 and 5, and I don't know the units of measure here, so let's just call it seconds. From 2 to 5 seconds, we're moving in a negative direction. At t equals 5, we're turning. You have to stop to turn. And then forever and ever, we're going to be moving in a positive direction. And the number line here is representing that movement as well. All right? Positive direction, negative direction, and then back to positive direction. Okay? Now let's take a look at our acceleration, graph of acceleration. So to find the equation for acceleration, you take the derivative of velocity, which is the second derivative of position. All right, so the derivative of 6t squared minus 42t plus 60, that's just going to be 12t minus 42 using the power rule. All right, we're going to find our critical points by setting our equation equal to 0. All right, so 12t minus 42 equals 0. All right, add 42 to both sides, divide by 12. 3.5 is a critical point. Right? So now we're going to analyze our acceleration and compare that to the velocity. So we have one critical point at 3.5. we only need to plug in one value between 0 and 3.5. However, we've got a critical point for velocity at 2 and a critical point for velocity at 5. So if we want to be able to analyze speeding up and slowing down, we're going to need the sign of both acceleration and velocity, right? So we're going to need more than just our typical 1 point in between each interval. We're going to need it on every interval for both velocity and acceleration. But if we plug in any value that is less than 3.5, we are going to get a negative value, right? So if I were to plug in 1, for instance, that would be 12 minus 42. That's negative. If I plug in any value greater than 3.5, we get a positive value. So now let's take a look over here at our graph of acceleration, right? So notice that where acceleration is negative, right? Our acceleration curve is below the x-axis. At 3.5, we have an x-intercept. Right? Notice it was a horizontal tangent for the velocity curve. So critical points are x-intercepts for velocity acceleration, for velocity and acceleration. So what's a critical point? 3.5 for acceleration, 2 and 5 for velocity. Those are our x-intercepts. Right? So now, if we compare what's happening for the velocity and the acceleration on each of our intervals, so between 0 and 2, so 2 is a critical point for velocity, between 2 and 3.5, a critical point for acceleration, between 3.5 and 5, 5 is a critical point for velocity, and then more than 5, we can determine whether the graph is speeding up or slowing down. Right? So everywhere from 0 to 3.5, acceleration is negative, right? We see that in the graph. Velocity, though, is positive on the interval from 0 to 2. So notice our signs do not match for acceleration and velocity. So that means the object is slowing down. When the signs don't match, right? When they are different signs, the object is slowing down. So from 0 to 2, the object is slowing down. For values greater than 2, velocity is now negative. Acceleration is still negative, but now velocity is negative. The signs match, the object is speeding up. Right? So for values, and now so we're still in the same interval as far as velocity is concerned, right? So velocity is negative on that whole interval of 2 to 5. Acceleration changes at 3.5, right? And goes from negative to positive. So now the acceleration is positive, the velocity is negative, the signs don't match, it is slowing down. And then for all values greater than 5, both velocity and acceleration are positive. That means the object is speeding up. And then we see that in our table right here. All right, so from 0 to 2, the object is slowing down. From 2 to 3.5, it's speeding up. From 3.5 to 5, it's slowing down. And anything greater than 5, it is speeding up. So we can use our velocity and our acceleration equations to be able to describe the movement of an object. We can also compare that with graphs, and we can use graphs to describe the motion of an object. And there's just some important things to know. One last thing for me to say before we look at solving some problems together. And we won't always graph everything, but when you have a graph, you should be able to analyze it. Notice that a horizontal tangent on the position is an x-intercept on velocity, and a horizontal tangent on velocity is an x-intercept on acceleration. Right? Just bear that in mind so that you can actually describe acceleration from your velocity curve. Right? So here we can see that. Notice that the velocity is decreasing, has a negative slope. So where your velocity has a negative slope, your acceleration is going to be negative. So remember, when on the position function, where the position function had a positive slope, the velocity would be positive. Where the position function had a negative slope, the velocity would be negative, and we see that in the graph. The one place where the velocity curve, where the position curve is negative, has a negative slope is from 2 to 5, and that's the one place where the velocity curve is below the x-axis. Notice that the velocity curve has a negative slope, not necessarily negative values, but a negative slope from 0 to 3.5. Notice that the acceleration curve is below the x-axis. So we can describe acceleration just by looking at the velocity curve. Notice that the velocity curve has a positive slope from 3.5 to infinity, and notice the acceleration curve is above the x-axis from 3.5 to infinity. So just some things to note. All right, we're going to do, I think I had one problem and the rest were taped. And this is my one problem, I think. So I had previously done a video, actually a while ago, and I'll use that video, but let's do one problem together. Did I move back? Yeah, all right. So a particle moves along a horizontal line. Its position function is s of t for t greater than 0. Greater than or equal to 0. For each problem, find the velocity function. All right, so and then we're going to do a little bit more than that because that's just way too easy. All right, way too easy. All right, so v of t, which is the derivative of the position function, would be, so just take the derivative. That's just going to be negative 4t cubed plus 45t squared. To find the velocity of the function at t equals 2 seconds, you just plug in 2. All right, so that's going to be negative 4 times 2 cubed plus 45 times 2 squared. So that would be negative 32 plus, all right, so 4 times 45 is going to be 180. So that's going to be 148. And it would be nice if there were units here. Let's call this meters per second. It's moving fast. All right, so this would be, so meters and seconds are our units. This would be meters per second, just to practice units. All right, so by the velocity, we can see that our object is moving in a positive direction. What's the acceleration of the what's the acceleration of the particle at t equals 2 seconds? All right, so now we want a of t, which is the derivative of velocity. All right, so that would be negative 12t squared plus 90t. All right, and now we'll evaluate it at 2 seconds. All right, so that's going to be negative 12 times 2 squared. And by the way, I think these are all in your notes. The question, I don't know if I put the questions in. I probably did. If I didn't, just add the questions. Negative 12 times 2 squared plus 90 times 2. That would be 4 times negative 12. That's going to be negative 48 plus 180. And so that's going to be 132. And this would be meters per second squared, because that looks nicer than, you're not wrong to say meters per second, right? But I think it's just a little easier to say meters per second squared. Right? And so we can see we have positive acceleration. Is the particle speeding up or slowing down at t equals 2 seconds? So we're not just going to say yes, speeding up or slowing down. We're going to say why. All right, so the particle is speeding up because both, and it's fine to put v of t. We've identified that that's our velocity. You can write velocity. I'll do both. You pick. All right, or we'll do both. And a of t, which is acceleration, are greater than 0, all right, at t equals 2 seconds. We should be precise. If we just said they're greater than 0, is that implying they're always greater than 0? Right? But it's greater than 0 at t equals 2 seconds, and that's the only time we cared about. Okay? So it's not too difficult to determine speeding up or slowing down. You simply find the equation for you find the function for the velocity curve, which is just the first derivative. You find the equation for the acceleration of the particle, and that's just the second derivative. And then you evaluate for some time. And if the two signs match, the object is speeding up. If the two signs are different, then the object is slowing down. Thought there was something over here. Oh, same thing we want to know is speeding up or slowing down at t equals 8 seconds. All right, so I guess I erased this. Let's find our questions here. So first of all, we need to find the velocity. So to be able to answer that, we have to find v of t, and specifically, we have to find v of 8. All right, so that's v of t is the derivative of the position function. That will be 4t cubed minus 36t squared. I thought it was the same equation, but I realized no, it's not. All right, and then we want to take we want to plug in for 8 seconds, and then I'll do that over here, and then we'll take the second derivative. So v of 8 is 4 times 8 cubed minus 36 times 8 squared. Oh, hope I have a calculator handy. 8 cubed is 512. I'm going to have to write it down because I'm not going to remember all this in my head now. And 36 times 64. Yeah, I can do 4 times 512. That's going to be 2,048, I think. But I cannot do 36 times 64 well in my head. I can break it down and do 30 times 60 and break it down to a bunch of products, but really, this lesson is not about me doing mental math. Okay, my 4 times 512 is right. I just want to double check. 36 times 64 is 2,304. All right, so that's going to be negative 256. All right, so we found our velocity. Let's find acceleration now. So find a of 8. All right, so that would be, we take the derivative, so a of t is 12t squared minus 72t. All right, now we'll find a of 8. So that's 12 times 8 squared minus 72 times 8. So 12 times 64. Oh, something's definitely wrong. I must have hit something in there because it's not 17. I really don't think it's 17,000. I'm pretty sure it's not. I feel quite sure it's not. It's 768. I mean, I don't think it's that big. 72 times 8 minus 576. So that's going to be positive 192. All right, so now, and actually let's put our units. I'm sorry, I forgot the units. That will just keep meters per second. And then this one is meters per second squared. Notice they are not the same. So is our particle speeding up or slowing down? The particle is slowing down because v of t, and I meant to put a of t, not 8 of t. A of t have different signs when t equals 8 seconds. Right? We've given our answer, and we've explained why. You always want to justify your answers. It's not enough just to answer. All right? And so this is where I'm going to stop, and you can see some more problems like this in the next podcast. Thanks for watching. Bye for now.